Assalamu alaikum once again. We're back with another video lesson. In the previous video lesson, we did cover the magnetic field strength and the magnetic field direction for wire, for coil, and for solenoid. And of course, we went through a lot of equations and we solved a lot of questions. And of course, we gave some ideas as well. We talked about Earth's magnetic field. We talked about how a compass would align itself with Earth's magnetic field line so that it can show the, let's say, the direction or Earth's geographic north and south pole, let's say. Today we'll go through a new concept, which is basically the magnetic, you can say the magnetic force, yeah? So what is a magnetic force? To begin with, of course, we're going to start with charged particles in a magnetic field, or what happens when a charge is inside a magnetic field, yeah? That is basically what we're going to focus on in this lesson. Okay, so now, before to explain this, let me talk about what happens when there is a charge inside a magnetic field or when there is a charge moving into a magnetic field. Okay, now experiments have shown that, let's say we have a magnetic field, okay? Let's use this color here, okay? And of course, let's increase the thickness of the pen here. Let's say we have a magnetic field, by the way. You've already learned that. Across it means into, yes? Okay, and if it is a point, that means out of, let's say, okay? Out of. So let's say this is a page. Across it means into the page, and of course a point, it means out of the page, because we're going to need this one when we are talking about the magnetic force, because it requires a lot of these understandings. Okay, so let's say that we have a magnetic field. This magnetic field is into the page, okay, as you can see here. Into the page, yes? So experiments have shown that if we have, or if there is basically a charged particles, let's say, and if this charged particles, if it is inside, let's say, if this charged particles is inside the magnetic field, but if the charged particle is not moving, or if the magnetic field is not changing, then this charged particle will be affected by no force. In another word, there will be no force acting. By the way, there is something called a magnetic force, yeah? Or before that, I can tell you that if a charged particle is moving into a magnetic field, it will experience a force, yeah? That is basically the concept for today. But to begin with, we'll talk about different cases. For example, the first case, if you have a magnetic field and if you have a charge inside the magnetic field, but if, like, what happens if this charge is not moving, or if the magnetic field is not moving, let's say. And if that is the case, then we can say there is no net force acting on this charge here, or you can say the magnetic force on this charge is 0. Okay, now that is one of the first cases or scenarios that we can have, yeah? What happens if we change the case in here? For example, let's say, again, we have a magnetic field, by the way. Okay, so once again, we have a magnetic field. Let's use blue again. So we have a magnetic field. But this time, the charge is moving inside the magnetic field, let's say. Okay, so these are basically demonstrated by experiments, yeah? So if, let's say, we have a positive charge again, let's use red for the charge. By the way, it could be a positive charge or a negative charge. In terms of the magnitude of the force, it doesn't make any difference here. But in terms of the direction of the force, that is a different story. We'll get into that part later. So, if this charge is moving into the magnetic field here, you can say, so basically this is the direction of the magnetic field here, okay, if this is the direction. And of course, you can see that the direction of the magnetic field is into the page here. This is basically, imagine this is going into the page, or you can say, basically, this is the direction of the movement, and this is the direction of the magnetic field. So you can see that the direction or the angle between the two is basically 90 here. So if I do this, that is 90 between what? Between V and between the magnetic field strength here. If that is the case, then this charge will experience a magnetic force here, but this magnetic force will be maximum on this charge. That when will it be maximum? If this charge is moving, let's say, perpendicular to the direction of the magnetic field here. That is the second case, yeah? Now we have another case, let's say, what happens if the magnetic field lines, let's use blue again. So here's again the magnetic field lines, yeah? Or as a matter of fact, I'll draw it in different ways. What happens if, take a look, this is the direction of the magnetic field lines. That is basically to the right. Okay, these are the direction of the magnetic field lines here. What happens if this charge is moving parallel to the direction of the magnetic field? So here's the charge, it's positive charge, it is moving parallel to the direction of the magnetic field. So if these two are parallel, we can say V, the charge is basically, or the speed of the charge, or the direction of the charge is basically, charge moving is parallel to the direction of the magnetic field. In this case, this magnetic field will experience no force at all. So we can say the magnetic, by the way, these have been demonstrated, or you can say experimented, and this is basically what they have found. So experiments have shown this, by the way. So if a charge is moving through a magnetic field but parallel to the magnetic field, then of course there will be no magnetic force on this charge, or this charge will be affected by no magnetic force in here. Now there's one more case here. So basically it is maximum if it is at right angle, it is minimum or zero if it is parallel to one another. And of course it is zero if the charge or if the magnetic field lines are not changing here. And then there is, let's take one more case here. Let's say here's the direction of the magnetic field line one more time. So let's use this one here. Okay, so blue. Okay, so here's the direction of the magnetic field lines. Okay, so this is B. And let's say we have a charge, once again, but this charge is basically moving at an angle to the direction of the magnetic field here. And of course, this velocity, you can say, because it is at an angle here, it can be analyzed to different components, let's say. So we're going to use this one to analyze this too. Perhaps let's use different color. So this one is going to be analyzed to two components. One component is going to be parallel to the magnetic field, and the other component will be perpendicular to the magnetic field. We know that this component would basically be parallel, so the magnetic force on the charge will be zero on this component here, but then the other component that is going to be F, or you can say B, let's just say, let's use V, all right, sine theta in this case. Let's go back one more time. Right, so let's say this is the perpendicular component. If this is the angle, then for this one here, we can say V sine theta, okay? And of course, you can go with B sine theta in this case, let's say, but we don't want that. We'll just go with V sine theta because basically the angle is between V and basically the magnetic field here. So, but this component is perpendicular to the magnetic field here, but because it is at an angle, so of course there will be a magnetic force on the charge here, but this magnetic force is not going to be maximum and it is not going to be zero. So it's basically going to be between zero to maximum here, okay? But it is not one of these two, yeah? So of course you can say excluding, all right, these two parts. So it's going to be somewhere in between zero, okay, bigger than zero, but smaller than maximum here. When does this happen? If this charge is moving at an angle into a magnetic field here. Now there is one more thing we can add up to this one here. Okay, we can say if this angle theta is 30, then of course, then this magnetic force is going to be half of maximum, yeah? Half of maximum will be if the angle between V and B is 30 degrees, or you can say 150, that is also the same thing here. Now because we're talking about the angles here, so we can say the magnetic field is going to be, or the magnetic force on a charge will be maximum if the angle between the two is 90 degrees, or instead of 90, we can have 270 as well. These are in degrees, yeah? So when will it be zero? It's going to be zero if the angle between the two is basically zero, or it could be, for example, instead of moving this direction, it could move the other direction, and of course the angle is going to be 180. So when the angle theta is 0 or 180, then of course we can say the magnetic force on the moving charge is going to be 0 here. So these values has been, let's say these values, okay, have been shown by experiments that this is what happens when a charge is going into a magnetic field, by the way. And then Later on, we'll study, for example, will this charge, once it will experience a magnetic force, will it continue moving like in a straight line? The answer will be no, but of course, we'll go through this one in detail soon, inshallah. So now we can go through these points, yeah? So charged particles in a magnetic field. Experiments show that a constant magnetic field does not experience, let's use, so what type of field? A constant magnetic field. That means a magnetic field that doesn't change, does not experience a net force on a stationary charged particles. That is one. Second point says charges moving through a magnetic field will experience a magnetic force. This force will be maximum when the angle between, let's say, the magnetic field and the direction of the movement is right angle, let's say, or 90 degree. If it is 90 degree, the force will be maximum. If it is parallel to one another, then the force will be minimum or zero. So the force has its maximum value when the charge moves perpendicular to the magnetic field, decreases in values to other angles, that means less than 90, and of course it becomes zero when the particle moves along, or you can say parallel to the field lines. Parallel, that means if the angle is basically zero with the magnetic field lines. Okay, now, a charge moving through a magnetic field experiences a magnetic force. Now, so far we've mentioned that if a particle is moving into a magnetic field, it does experience a magnetic force. But how big is this magnetic force? Is there a certain value where we can find? Yes, and of course, we have these equations here. So a moving charge experiences a force that is perpendicular to both the magnetic field and the direction of the particle's motion. Okay, so remember this. Now, we said there is basically, in order to get maximum force, the charge or the direction of the movement must be perpendicular to the magnetic field. But this force that is basically the charged particle will experience will be perpendicular to both of these two. What do you mean by both of these two? That means the force will be perpendicular to both the magnetic field and the direction of the movement, you can say. Okay, so we can say, we'll talk about this one. So the force will be perpendicular to both the magnetic field and the direction or the speed of the particle, or the direction. Okay, so perpendicular to both. To find the magnetic force on a charged particle moving in a magnetic field, of course, use these two equations, or you can say this, yeah? So now let's talk about this one in a second. So how do we find the magnitude of the magnetic force in here? All right, so let's get this one done. Okay, so how do we find this? Take a look, guys. We said there is a magnetic force. So this magnetic force here, we can use M, all right, to stand or to represent the magnetic force here. This magnetic force equals to Q, that is the charge, multiplied by V, that is the speed, all right, of the, or you can say the velocity of the charge, because we're concerned with the direction as well, and then multiplied by what? Multiplied by the magnetic field strength here. So we can say QVB. If we have, basically that is the equation that we use most, yeah? But whenever angles are given, then you can add this part, sine theta, to the equation as well. Once again, when do we use this part? Normally, most of the situations that we have, the charge will move perpendicular into a magnetic field. But if it is not perpendicular, then of course, if it is perpendicular, sine 90, you do know that sine 90 is equal to 1, so you don't need to write this part. But if angles are given, which is not 90, then of course, you need to have sine theta with the equation as well. That is, when do we use this? If a charge is moving, let's say, into a magnetic field, let's say. So here's a magnetic field, okay? This charge is moving into a magnetic field, then how much force will this charge experience can be found using this equation right here. So, but that is, watch this. So what are each one of these letters? Basically, that is the force this charge will experience, and that is measured in Newton. We do know that. And this Q stands for the charge, because we have a charge basically that goes into a magnetic field. And the value for this charge, or you can say, first of all, this charge is measured in Coulomb. You do know that, grade 11, yes? Okay, and the value for this charge, basically, whether it is a proton or electron, it doesn't matter. Their magnitude, or the value for their magnitude, is still the same, which is 1.6 times 10 to the power negative 19, okay? That is in coulombs. We're talking about the magnitude, by the way, not their direction, because if it is positive, that is different. If it is negative, that is a different story. But in terms of their magnitude, it is both the same here. That is basically, we can say Coulomb here. What about V? V basically is the speed, you can say, or the velocity of the particle, which is basically measured in meter per second. What about B? B is basically the strength of the magnetic field, and that is measured in Tesla here. Okay, so basically that is what we have, yeah? The force that this charge will experience is basically equal to QVB, and then these are their units. But remember this equation just tells you that, for example, if a charge is moving, what if more than one charge is moving? Let's say 2 charges or 3 charges are moving into a magnetic field, yes? That is also a question here. Most of the questions that we're using, most of them, are 1 charge, so we just use QVB, yeah? But what happens if it is more than 1 charge? Then in order to find the magnitude of the magnetic force, then if it is 1, we'll just say 1, yeah? If it is more than 1, then you can add an n here. What does this n represent? This n represents the number of charges. For example, if it is 1 charge, we just use Q. If it is 2 charge, then we can use, for example, 2 times Q. If it is 3 charge, then we use 3 times Q, and of course, so forth if it is more than that, okay? Okay, so this is basically what you need to know about or regarding the magnetic force in here. But if we want to find the strength of the magnetic field here, basically, if we want to find B here into the equation, then make B the subject, yeah? So B equals to what? B equals to N, or let's say the force, not N, the force divided by what? Magnetic force divided by Q, and of course by V as well. So we can say the strength of the magnetic field equals to force divided by the charge, or you can say number of charge multiplied by the velocity. By the way, if we are concerned with the magnitude, then we can just say speed. We don't have to go with the direction here as well. Okay, so, but now let's do some unit manipulation as well. Okay, we do know that, or we've studied that B is basically measured in Tesla. I don't know, I feel like today I'm about to go with basically instead of basically. Okay, so take a look here. So that is basically B in Tesla, correct? Do you agree with me? So we can say Tesla is equivalent to force is measured in Newton, charge is measured in Coulomb, and then speed is measured in meter per second. Okay, very good. So this is another unit for Tesla. We can say Tesla is equal to Newton Coulomb meter per second. Okay, but let's do more. Grade 11, you've studied that current is basically equal to charge over time. In another word, Coulomb per second. Okay, Coulomb per second. So what happens if I move this second under the Coulomb? Can I do that? Yes, so it becomes Newton over Coulomb per second meter. But Coulomb per second here isn't that equal to the current, and current is basically measured in amperes. So can I rewrite this one as Newton ampere meter? The answer is yes, okay? Now, there is more, by the way. We'll get into this one in the next page here, but I just wanted you to know this much for now here. Okay, so we have a question says, what does the magnetic force depend on here? Now, once again, whenever it tells you what is one thing depends on, if there is an equation, always write it down. So magnetic force equal to what? Equal to QVB, yes? And of course, we can say sine theta as well, because now this one with effect would be one of the factors that this force depends on. So we can say depends on what? Depends on the charges, or you can say depends on the charge basically, or the number of charge. That is also could be fine, yeah? It also depends on what? Depends on the speed of the particle, yes? Remember this, we're talking about the magnitude, okay? Okay, so what else does it depend on? It depends on the strength of the magnetic field as well. Yes, very, very good. What about this angle here, or sine theta? This sine theta is normally between V and B here, yes? So we can say it depends on the angle which is between the velocity, the speed, and the magnetic field strength as well. Because remember this, we said if theta is 90, then the force is maximum. If theta is 0 or 180, this force is minimum here. If theta is basically 30 or 150, then of course is going to be half of maximum. So of course this angle between V and B, it would affect the magnetic force as well. So we can say magnetic force depends on this 3 plus the angle, That is 4 factors that could determine the strength of the magnetic field. Okay, now, how do we define one Tesla? We said magnetic field strength, it depends on what? It depends on, we said a new way to define magnetic field strength, we said it's measured in Tesla, equals to magnetic field equals to QV, yes? So, and of course, let me erase this one here. We can say, oops, erased too much. Okay, so we can say if this is basically, if the force is 1 Newton, if the charge is 1 coulomb, and then if the speed is basically 1 meter per second, then of course multiplying all this, 1 coulomb times 1 meter, and then 1 Newton divided by this equals to 1 Tesla, yes? So how can I define 1 Tesla? I feel like I need to write this one a bit nicer so you understand what we are talking about here. So basically, all right, so take a look, 1 Newton divided by 1 coulomb and then multiplied by 1 meter per second. Okay, so using this, is there a way, or can you define 1 Tesla based on this equation or what you see here? Yes, all right. So how do we do that? We can say 1 Tesla. It is basically, we're talking about the direction, we're talking about the magnitude, not the direction. So can I say 1 Tesla is basically the magnitude of the magnetic field strength? Yes, we're not talking about the direction, by the way. We're just talking about the magnitude. So I can say 1 Tesla, it is the magnitude of the magnetic field strength, yes? When a charge of 1 coulomb, all right, is moving perpendicular, because we're not talking about sine theta, we remove that, assuming that it is perpendicular, or the angle between, let's say, V and B is perpendicular, yeah? So we'll say, when a charge of 1 Tesla is the magnitude of the magnetic field strength, when a charge of 1 coulomb moving perpendicularly into a magnetic field with a speed of 1 meter per second, then of course it will be affected by a force of 1 Newton, you can say, or it will experience a force of 1 Newton. So let's repeat this one more time. How much is 1 Tesla? How big is 1 Tesla? We can say 1 Tesla is basically is the magnitude of the magnetic field strength, not the direction. It is the magnitude, the value of the magnetic field strength, okay, when a charge of 1 coulomb is moving perpendicularly into a magnetic field at a speed of 1 meter per second, then it will experience a magnetic force of 1 Newton. Once again, is the magnitude of the magnetic field strength when a charge of 1 coulomb moves into a magnetic field, moves at a speed of 1 meter per second into a magnetic field or perpendicular to the magnetic field, then it will experience a force of 1 Newton. I hope that was easy and of course clear enough. Okay, take a look at this study tips. This is also very important. It says what? The magnetic force, okay, is equal to QVB sine theta, okay? And that is, of course, when is it maximum? We said it is maximum if the angle between V and B is 90, yes? Or another angle that is equivalent to 90, you can say that is 270, yeah? Or sine 90 and 270 would be basically, gives you the same thing in this case. Okay, so we can say maximum. When is the magnetic force is maximum? When the angle theta between V and B is 90 degrees. That is this. Or we can say 270, because all sine angles are the same thing here. We did have, went through this one for many other examples, okay? So when will it be half of maximum? That is if the angle is 30, sine 30, or sine 150, because this two would also give you half of maximum. When will it be 0? Of course, it will be 0 if sine theta is 0 or 180 degrees. At these two angles, we know that the sine theta will be 0, so there will be no magnetic force. Another way to put that into context is we can say when the charge is moving parallel to the magnetic field. Okay, now for question 15 here says, can a stationary magnetic field set a resting electron in motion? Explain your answer. Of course, we said that if there is a charge that is not moving, if it is at rest basically, and if the magnetic field is not changing, then there will be no force on the charge. And if there is no force on the charge, that means the charge will stay at rest forever, let's say, and unless an external force acts on it. Okay, so in this case, well, the answer is going to be no, because magnetic fields apply a force only on a moving charge. Okay, now, another question which is also important says, when will a particle experience no magnetic force? All right, can you count a few ways where the particle experiences no magnetic force? I've covered a few ways so far, and of course there is one more we can say, yeah? So, but what about you? Can you tell me any other ways without looking at the answers? I hope yes. Okay, so one of the ways where we can see a charged particles, or when a particle experiences no, when a particle, we didn't say, or sorry if I said a charged particle, yeah? So when will a particle, when we say a particle, that means it could be either charged or even not charged. It's just a particle, yes? If that is the case, when will a particle experience no magnetic force? The first one we said, if the charge is not moving. If the charge is at rest, the particle will experience no magnetic force. Another way we said that, for example, if the charge is moving parallel to the magnetic field, if the angle between V and B is 0, then of course the charge will experience no magnetic force. And there is another way, yeah? And the third way is if the particle is not charged. For example, like what? Give me the name of a particle that is not charged. Protons are positively charged. You can say electrons are negatively charged. What about neutrons? You see that, I mean, you already know neutrons are neutral, yeah? So of course, if they don't have any charge, then of course they will experience no magnetic force, no matter what are their orientation. They could be moving parallel or perpendicular inside a magnetic field, whatever. But if that is the case, if they don't have any charge, they will experience no magnetic force. So these are the three ways where a charge can experience no force, yeah? Or no magnetic force, we can say. If the charge is not moving, stationary, or if the charge is moving but parallel to the magnetic field, or if the particle is uncharged, okay? Study tip, remember this, it says the magnitude of the charge of the electron and proton are the same. Remember, we're talking about their magnitudes, yeah? And of course it is about 1.6 times 10 to the power negative 19 coulombs. And the mass of proton, it is about 1.67 times 10 to the power negative 27 kilogram. And the mass of electron, which is way, let's say, lighter compared to the mass of a proton, it is 9.1 times 10 to the power negative 31 kilograms. Okay, now an alternative right-hand rule can be used to find the direction of the magnetic force in here. Okay, now so far in the previous section we did talk about how we can find the direction of the magnetic field, let's say, or magnetic field strength by using the right-hand rule, yes? So but this time here, what happens if a charged particle, let's say, go into a magnetic field, yeah? Of course it will experience a force, but can we find the direction of this force? Like, can we, or is there any other, or is there a way where we can use to find the direction of the magnetic force? Let's say if B and V, or the direction of B and V were given, or can we find the direction of each individual if the other two are given? The answer is yes. So what are we going to use? We're going to use our right hand again. But how are we going to do that here? This time, remember this, and this is a must, you need to memorize this. Remember, thumb would be basically, how about if we start with the fingers first, okay? Finger must always be in the direction of the magnetic field. So this is magnetic field, don't forget, okay? And then your thumb will be in the direction of the motion here, the speed in this case. And of course, your palm, all right, would be the direction of the magnetic force, okay? But remember, we have protons and electrons, yeah? So every time you're going to use your right-hand rule for the magnetic force, make sure that you have a pencil or a pen in your hand. And this is how you're going to hold it, okay? Or it could be like this, it doesn't matter. So remember this. This is the direction of the magnetic field always. You're going to align this or this direction the same as the direction of the magnetic field. That is one. Second, your thumb must be pointed in the direction of the charge movement, or the speed of the charge, the velocity in this case, because we're talking about the direction here. And then your palm would represent the direction of the magnetic force on a positive charge, like proton, for example. Okay, or it could be a positive ion or whatever. Okay, so in this case here, the palm would be representing the direction of a magnetic force on a positive charge. The back of your hand would represent the direction of the magnetic force, but on a negative charge, like an electron, for example. So let's give an example and see how we can find the direction of the magnetic field here. So for example, let's say, let's give you an example here. Let's say we have, let's use this. So let's say here we have the direction of, let's say, a magnetic field, which is into, let's say, the page in here. Considering this screen as a page, let's say, okay, we can do this, let's say, to make it look like more, or look more like a page here. Okay, so this is the direction of the magnetic field, which is, let's say, into the page. Okay, we can reverse the direction in a second. We'll do that as well. And let's say that there is a charge moving. This charge, there is a charge moving, let's say, to the right of the page. If this is basically, we can say up the page, this is down the page, and this is, let's say, right of the page, and the other side is basically left. And of course, this could be into the page, and this is out of the page. If that is the case, then what is the direction of, basically, this is the direction of V, and this is the direction of B, as you can see here. So what is the direction of the magnetic force on this charge? It is a positive charge. So here's what you're going to do. Look, what is the direction of the magnetic field here? It is into the page, yes? So we're going to use our right hand, by the way. So it is into the page, yes? So here's what you're going to do that. But what's the direction of the motion here? If I do this, that means the motion is upward. Is that the case? No. So I'll have to flip my hand or align my hand so that this thumb would point the direction of the motion. So now it is correct. But what is the direction of the force in this case? We said whenever you are trying to find the magnetic field strength or the force, the magnetic force, always have a pencil or a pen in your hand, and you can do it this way, yeah? So the palm would be the direction on a positive charge, the force, of course, and the back of the hand would be the direction of the force on a negative charge. So if that is the case, watch this, into the page. I'll do it this way so that this would represent the direction of the velocity here. Okay, so now this pen basically points upward, and that is, we said the palm would represent the direction of the magnetic force on a positive charge. So in this case, when this charge is moving into a magnetic field, of course it will experience a force, and this force will push this charge upward here, and which makes it move this way here. What happens if the charge was negative, let's say? If the charge was negative, let's erase this one as well. What happens if the charge is negative? We can erase this one too. If the charge is negative, let's have another charge here, but this time we are using a negative charge. If that is the case, let's say it's moving in the same direction, yeah? So we're going to hold the pencil again. That is the magnetic field into, but look at the direction of the motion. So it has to be this way. So magnetic field into the page, the motion to the right of the page. So look, if it was a positive charge, the force will be upward, but because it is a negative charge, so there will be a force downward on this one. So this electron would be applying or experience a force which makes the electron to move downward here. So this would be the direction of what? The direction of the magnetic force on both the positive charge and the negative charge as well. Can I use, for example, the table that we have used in the previous section? Yes. And how can we do that? You can make a simple table like this. Remember, each one of these has to be at a right angle to one another. So we can say this is B, and this is V, and this is, I think I'll go ahead and ignore this column here. So let's use this one here. So basically this is B, and this is V, and this is F, okay? But remember, this F could be for a positive or for a negative charge. So we can try this with the first one, yeah? We can say, by the way, can use X and Y, Z axis here. So for the magnet, it is into the page. We said if it is into the page, that is negative Z, correct? Do you remember this? I hope you do. So let's say this is negative Z here. What about for V here? So V is basically, it is moving towards the positive X axis. So remember this, and these are, for example, this is Z, this is X. So the other force, or the force must be on, y-axis, yeah? But remember this, is it y positive or negative? That is what you need to determine. And in order to do that, you need to know whether the charge is positive or negative, okay? So remember, these has to be at right angle to one another. So because it is a positive charge, so I can do this, yeah? Magnetic field is basically into z, right? Negative z, that is into the page. Velocity on x-axis here. So if I do this, basically, if it is a positive charge, by the way, so of course it's going to be y positive, yeah? So I'll do the same thing. If it is a negative charge, basically it is going to be y negative, yeah? So if it is a negative charge, yeah? This is basically for negative, and this is basically for positive. What happens if we flip the direction of the magnetic field in here? So let's do this one as well. Perhaps this will be the last example in this regard. And then once we go to other examples, that'll be the same as a practice. Let's say here is, once again, this is the same as the plane of a page. So these are, this time, the magnetic field, we can say, let's use this. These are too big. Okay. So let's say these are basically the magnetic field strength, or the direction of the magnetic field strength, but this time you can see that it is basically out of the page, correct? And if that is the case, and let's use a different orientation for the charge movement here. Let's say this time, last time the charge were moving from left to right. This time, let's say the charge is moving basically from the bottom of the page, right, upwards. So what will happen in this case? So let's decrease the thickness a little bit more. I think this is too much. Okay, so here's a positive charge. It is going into a magnetic field. Okay, so let's see what happens, yeah? Once again, always have this, sorry. So have a pen or pencil in your hand. We said, remember, align your fingers same way as the direction of the magnetic field, yeah? And this should be the direction of this. So if I do this, you can see that my finger is pointing that the magnetic field is into the page. Is it into the page? No, it is out of the page. So I'll have to, let's say, change the way that I'm holding, let's say, or holding this, or representing the direction. Now you can see that the direction of the magnetic field is out of the page. That is towards you in your perspective. If that is the case, look at the direction of the movement here, yeah? So V is basically upward here. If that is the case, and if I have a positive charge, remember, the palm is for positive. That means this charge will get or experience a magnetic force, and that is basically going to be towards the right of the page. Remember, this is right, and this is left, this is up, and this is, let's say, down. Okay, so if that is the case, one more time, yes? So outward, that is the magnetic field. The motion is upward, then this, watch this, the palm is the magnetic force on a positive charge. So we can say the magnetic force is basically towards the right, you can say, or to the right. Using our capital to emphasize on this here. Okay, so can we use the table? Yes, okay. We can use the table as well. We'll say the magnetic force is basically B and V and F as well. B is basically positive Z because it is out of the page. And this one is positive Y, yes? Watch this. Z, Y, so this one has to be X. But is it X positive or negative? Once again, you have to use your hand to do this. So this is Z positive, Y positive. So a positive charge would experience a force to the right, then that is X positive, yeah? But if it is a negative charge, everything would be the same, except then the charge will, let's say, will deflect in the other direction. So whenever we have a negative charge, that is going to be the same as if it is the reflection of a positive charge. So in this case, the charge will be deflecting this way here, okay? If it is a negative charge, it would have gotten deflected to the other direction here. So we can say, or if I just draw a little bit nicer here, if I remove this one here, imagine if it was a negative charge in here, it would have deflected in the other direction here. By the way, after it moves out of the magnetic field, then of course it can continue in a straight line if it is not affected by any other magnetic field lines. Okay, so let's make this one something like this. Then of course it can continue like this, and then here it can continue like this one as well, because it is not affected by any other magnetic field. So we can see that this is for magnetic negative, yeah? This is positive. So we can say this is basically, it's almost like the reflection of the positive charge, yes? And this is basically how one way you can guess the correct answer always when it comes to directions. Okay, we have a Wuzari questions. It says what? The magnitude of the electric force, okay, the magnitude of the electric force on a charged particle that is moving inside a uniform magnetic field is 0 if the angle between the direction of the particle the particle's velocity and the direction of the magnetic field is equal to what? So the magnitude of the electric force on a charged particle here, this, by the way, is supposed to be magnetic force, yeah? Let's change this one to, instead of electric, we'll make it magnetic. All right, let's just see if it agrees with the contest. The magnitude of the magnetic force on a charged particle that is moving inside a uniform magnetic field is 0 if the angle between the direction of the particle velocity and the direction of the magnetic field is equal to what? Is equal to when will this magnetic force will be 0? It will be 0 if the angle between V and B is 0, yeah? That is basically what it is. When will it be maximum if the angle is 90? When will it be half of maximum? You might say 45, but no, it is at angle 30, okay? Because sine 30 equals to half of the maximum. Okay, now take a look at these directions. These are for you, by the way. Just remember this. We have 4 sets of directions here. Each one of these directions could be given, okay? But remember, these are basically all the same, just in different words or names you can say. So I can perhaps go through this one all in once, yeah? So let's say, here we have a direction actually. We can go through this one, but let me just go through this like real quick on this. So watch this. We can use a direction or set of direction using x, y, and z direction here. So we can say, of course, this is y positive, y negative, x is positive, let's say, and of course x negative, yeah? And of course, if it is into, I think I'll have to use a thinner pen. And I hope you can still see this. Okay, if it is into the page, let's say, that is basically going to be z negative. If it is out of the page, it is going to be z positive. You are familiar with this, yeah? We can have another set of direction here. Instead of using x, y, z, we can use the coordinates. And what are coordinates? For example, like north and south, east and west, yeah? And of course, we can use this. But if that is the case, for example, let's say if this is the case, imagine this. If I face this way, that is north, and this is south, east, and west, yeah? In that case, if it is into the page, it is almost like equivalent if it is down, yeah? If it is downward and if it is upward, yeah? So if it is into, we can say this is going to be downward, okay? And of course, if it is, for example, perpendicular to that, it is going to be upward, we can say. And by the way, most of the time, we can use z negative for downward and z positive for upward as well. That is another set of direction, yeah? Another set of direction that we can have is this, for example. Let's say that if we are using the orientation of this, or if we are using the page of, let's say, something. If we're using a page, for example, let's say this is a page, yeah? If that is the page here, then of course this is going to be up the page or towards the top of a page, okay? Let's say top of the page would be better in this case. Top of the page. All right, this is going to be the bottom of the page. This is going to be to the right of the page. And of course the other side is going to be to the left. To the left of the page. And then for the third component here, we can say it is into the page, yes? Into the page. And of course here is going to be out of the page, yes? Out of the page. Oh, that is too small, but you can see that. And of course we can have one set of the direction, for example. If you're standing, let's say, on the equator, yes? Let's say the fourth one here, I can write it here. Imagine this is the Earth, and this is the equator, and you are basically standing right here. And if that is the case, for example, if this is me standing on the equator, that is going to be in front of me, okay? So we can say in front, okay? We can say behind. So for example, this is in front of me and this is behind me, yeah? And of course, we can say to the right or my right, or we can say to the left. And of course, what about the third component? If that is the case, watch this, in front of me, behind me, to my right, to my left. What about the third component? It's going to be above and below me, yeah? So you can say above, that is basically going to be perpendicular, yeah? So the third one is going to be above, and of course it could be below as well. So these are basically four set of components that you could be facing or you could be given in the exam here. But remember this, you can always interpret these axes, for example, into different components, and then you can get back to this one. I've explained this one before, but I wanted to re-emphasize on this one so that you know how it is done. Okay, and regarding this one here, I think we don't have a lot of time. Perhaps maybe I can do this one as the last thing for today, and then next time we'll continue from question 10. So let's see if we can catch up with this and doing this for today. So basically we talked about the magnitude of the magnetic field strength before. We said, not this. Okay, so watch this. We said basically magnetic force equals to what? Equals to QVB, all right, sine theta, forget the sign, if it is at maximum. Let's make this one quick a little bit. So B equals to F over QV, yes? If that is the case, the unit for B is Tesla, the unit for force is Newton, the unit for Q is, or charges, Q is Coulomb, and then for velocity is meter, for speed, meter per second. We said we'll bring this one here, then this one becomes what? Newton. Coulomb per second becomes ampere times meter. And of course, we can emphasize this or break it down furthermore. Newton is basically equals to what? The unit of force, and force is basically mass times acceleration. That is kilogram, you can say meter per second square, and of course divided by ampere, and then divided by meters as well. This two will cancel out. So this second goes down, so it becomes kilogram ampere second square. That is basically, these are all equivalent to Tesla. That is one. All right. We've also learned that we can say, previously we said that basically magnetic flux equals to AB cosine theta, yeah? So B equals to what? B equals to magnetic flux divided by area. In another word, Weber divided by what? Divided by area is basically meters squared. Weber divided by meters squared. Okay, that is this, yeah? But later on you will see that Weber, in chapter 6, we're going to study this, that electromotive force induced equal to negative and delta flux over delta T. This flux is basically Weber, so this is V and this is second here. So of course, instead of Weber, we can write voltage or volt second, and of course divided by meters squared as well. So this would be another unit for the magnetic field strength, you can say. So we've covered all this, yeah? And of course, there is one more thing here. We can also say that using this equation, we can say Newton, that is basically equal to Coulomb, meter per second, and of course Tesla as well. What else do we have? Or perhaps from this one here. Yes, we can analyze, or we can cross multiply this two. We can say Newton equals to, based on this, Newton equals to Tesla ampere meter as well, yeah? So these are basically some of the units we can have, and all can be gotten from Tesla and from what is the magnetic field equals to. So of course, there might be some units that you haven't got used to, but of course, along the way, you'll get familiar with all this, but try to be able to practice this because these are very important. So that is the end for this session. Inshallah, next time we'll continue from question 10. Till then, keep practicing, because that's what they say about practicing. Yeah, practice makes perfect. So make sure you ace it, or you just make it perfect. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.